We all know and love the video I made some years ago showing me interacting with my miniature GLaDOS. The one where I talked to her and she seemed to follow me around. To achieve this effect, I had to transfer the target servo positions from the control unit, a Raspberry Pi, to the body itself, an Arduino Nano. This communication was achieved by creating my own bus protocol named Simon, which stands for Scalable Independent Microcontroller Operating Network. In today's video, I want to deep dive into this protocol and develop it to a point where it is fast, memory efficient, and reliable. First, I want to re-establish the current state of the Simon protocol and explain a bit what is happening during transmission. In the old video, the communication was done by using two wires in total, one of which was used as a common ground. The other wire was used to transmit the actual signal. These two wires are connected to a pin on the Arduino and a pin on the Raspberry Pi each. One thing to note is that there is a logic level converter between the Pi and the Arduino because of voltage differences, but I will leave this out for simplicity. I will name the two pins that are connected to these wires the signal pin and the data pin. The transmission of data is achieved by converting the data to send into binary. Then, each binary digit is transferred by pulling down the voltage on the data pin for different time lengths. A 0 is represented by a single unit of defined length, a 1 is represented by 2 units of defined length. I coded this protocol in a way where this unit of length is a constant that can be easily changed. For this implementation, I defined it as 1 millisecond. There is some additional overhead to the protocol, like an activation and a finish signal, as well as another section where an ID is transferred. The idea behind is that each device that is connected to the Simon bus receives a unique ID. This way, each component can talk to another, as long as they know their IDs. Let me show you how this transmission looks like in the real world. For this example, I sent the string Hello World 2024 via Simon MK00. The result is this capture here that I recorded by hooking a logic analyzer onto the two wires. The software is called Logic 2 and I use version 2.4.14. Here we can see that the entire transmission took around 415 milliseconds. For the entire time, the signal pin was always pulled low. The signal actually starts with a sequence of 8 zeros, as can be seen here at the start. After that, the activation signal is sent in 3 milliseconds. This sequence of zeros was originally added because I had issues with the communication where it would just stop entirely at a random point. I will come back to the solution to this problem later. After the activation signal, the actual data follows. Finally, a finish signal as 4 milliseconds is sent. This is the current status that I want to improve. Mainly, I have 3 parameters that I want to optimize for. Dynamic storage size, as in RAM, program storage size, as in space to store the actual program into, and transfer time. To track improvements, I slightly restructured the overall program without changing the actual logic. This way I can let the compiler optimize away all the debugging parts and get the storage requirements for the actual code. This is luckily reported in the Arduino IDE every time you compile a program. I use version 2.3.2 for my tests, by the way. The time measurement is done in Logic 2, where I take a measurement from the first to the last wire change. The measurement is repeated 20 times to get an average. One thing to notice is that I actually had trouble even getting some measurements for the original version, because the protocol sometimes wouldn't work at all. Continuously resetting the Nano did the job though. All of the data presented just now is again shown in this table. You can see that I included some percentage numbers that need some explaining. For the program code and variable columns, the percentage relates to the total memory of the used Arduino Nano. For the time column, the percentage relates to the time from Simon MK00, aka the original state. This set of measurements and the explained inner workings of the protocol is now the baseline from which I will start my optimization. The first thing that I want to change is the usage of string objects to store the data in. Let me explain why. If you want to store a text character in memory, you usually need 1 byte for that. This 1 byte can represent 256 different characters. There's actually a table called an ASCII table, which defines which byte corresponds to which character. The data in this byte consists of 8 bits that can be 0 or 1 each. Together, they form an integer value that corresponds to the ASCII table. Converting between binary and decimal is a bit tricky at first, but once you know how to do it, it's fairly straightforward. If you want to convert from binary to decimal, all you need to do is go through the binary data and add together the powers of 2 of the 1 digits in the binary data. The powers of 2 correspond to the position in the binary data. I always help myself find the correct powers of 2 by thinking about the current power as the index of an array in which the binary data is. Important is that the power of 0, meaning 2 to the power of 0, is at the most right binary digit. Then, you increment the power by 1 by each digit you move to the left. Let's do an example, in this case value 157. The binary representation of this is 1, 0, 0, 1, 1, 1, 0, 1. We now go through the binary data in reverse, meaning that we start with the most right digit. Here, the decimal value is equal to 2 to the power of 0, which is 1. Since this digit is 1, we will add the value 1 to our result. Then we go to the next digit, which corresponds to the decimal value of 2 to the power of 1, which is 2. The digit is 0, so we don't add anything. The next decimal value is 4, and the digit is 1, so we add it to our result. We continue this process until we reach the most left value. The resulting calculation is 1 plus 4 plus 8 plus 16 plus 128. If we add everything together, we get 157, which is our starting value. To get from decimal to binary, the process is reversed. We start with the most left digit in the binary representation. Then, we simply divide the decimal number by 2 and check the result. If the remainder, meaning the rest that occurs when dividing with whole numbers, is 0, we mark the current digit as 0. If the remainder is not 0, we mark the current digit as a 1. We then move one digit to the right and divide by 2 again. We do this until the result is less than 1. This means that we have reached the final digit on the most right. If we do this for our example, we get the binary representation of 1, 0, 0, 1, 1, 1, 0, 1. Back to the previous code for Simon, what I was doing is that I took a string of characters and extracted the individual bits from the byte. However, I stored these individual bits in a new string, which was 8 times longer than the original data string. During sending, I looped over each bit and used the value in this char to determine whether a pin should be activated. This procedure does sound a bit weird, but somehow makes sense. I mean, it gets the job done of sending data over the wires. The problem arises if we take a look at memory management. A microcontroller has very limited programming storage and RAM. In case of the used Arduino Nano, it has only 30 KB of program storage and 2 KB of RAM. This is not a lot, and a problem arises if we use this version of Simon over a longer period of time. What I suspect is that for each transfer, the data string and binary string both allocate a new region of RAM instead of reusing the old region from the last transfer. This means that the RAM slowly fills up with data. This works fine until the RAM is fully allocated, but when the program wants to allocate even more RAM, the program crashes. This random crashing was a behavior I noticed and put a lot of hours into, because at the time I couldn't really figure out why it was happening. A temporary solution to even get the protocol to work was to add a serial print somewhere in the code, which is less than ideal. I want to solve these issues for good, and for this reason I want to start by changing the storage handling. I generally want to avoid using the string library as much as possible. Because of this, the input data is now no longer requested as a string object, but a char array instead. Even better, I only request the pointer to the first element to this array. This way, the minimum amount of data is copied when calling the send method, saving on RAM and thus improving stability. The conversion of the input data is actually entirely skipped because the individual bits are already available in the char array. I decided to constrain the protocol in terms of how much data can be sent over it by limiting the size of the byte array. The size is defined when setting up the protocol. Since the structure of the data to be sent has changed, I also need to change the way how the data is read and written. Instead of looping over characters in a string and comparing them against 1, the program now loops over the byte array, and for each byte, another smaller for loop is used. The smaller loop goes over the individual bits of a single byte and does a bit comparison of the most right bit. To get the correct bit at each loop, the current byte is shifted to the right. For reading, this process is the same, except that the byte is shifted to the left with each additional bit. With this upgrade, compiling the newly created version shows that it requires 2800 bytes of program storage and 310 bytes of dynamic storage. This is a significant improvement compared to the original version. When taking a look at the transfer times, the new version actually takes slightly longer than the previous version, roughly 5%. This is not a problem since currently I'm not optimizing for speed, but for storage instead. The actual reason for the time increase is the fact that in the original code, the answer from the receiver was not included, but in the new version. That means that this upgrade made the protocol fully working. In total, the goal of this version has been achieved, and the next version will be based on this version. The next thing that I want to tackle is the actual communication itself. As explained earlier, the protocol uses only a single wire to transfer the data. I want to change this to 2 wires, since having a common ground is mostly the case for most target applications. For my test setup though, I actually have to use a 3rd wire to establish the common ground. The basic idea for using 2 wires instead of just 1 is to still have 1 wire for sending the actual data, but the 2nd wire to provide a clock signal to know which data bit is coming next. This also means that instead of measuring signal lengths on the data line, the program waits for change on the signal line and then reads the next bit. I generally decided to work closely to how I2C is working, meaning that both lines are pulled high by default. A data bit is first configured on the data line and then the signal line is pulled low. This way, it is guaranteed that the correct data bit is on the data line when the signal line changes its state. Another change that I want to do is to remove the redundant signal changes before the activation signals, since these were an attempt to fix the issues with the original code and are not required anymore. Finally, the activation and finish signals are replaced. Instead of using different signal lengths, the data line is pulled low while the signal line is still pulled high. Compiling these changes shows the requirements of 2650 bytes of program storage and 312 bytes of dynamic storage. The small decrease in program storage is a welcome bonus. The more interesting change is the transfer time. The new program now takes 345 milliseconds, which corresponds to 83% of the original time. This improvement seems a little disappointing at first, but there's a simple change that can be done to make the signaling change a lot more worth it. The secret for making the previous change much more efficient lies in the timing of the data line changes. Currently, the data line is only changed for each low cycle of the signal line. This means that only half of the total transfer time a new bit is transferred. By adjusting the data line changes to both signal line states and letting everything else as is, let's see what the effect on our measurement has. Compiling gives the storage requirements of 2628 bytes for program storage and 312 bytes for dynamic storage. Again, a very small but welcome improvement. As promised previously, the transfer time cut nearly in half and now only takes 176 milliseconds or 42% of the original transfer time. This is the improvement I was looking for. Keep in mind that each signal change is still 1 millisecond long, just like in the original version. Taking a look at the recordings in Logic for this and the previous version, the effect becomes obvious. It is now much more difficult to differentiate the different protocol parts when looking at the recording by eye, but in my opinion this change is well worth it. The improvements until now are already pretty good, but I want to reach more. Next, I want to take a look at two different aspects, an attempt at reducing dynamic program storage, and a first test to check how fast the protocol can get. The general idea to reduce dynamic program storage is twofold. First, to reduce the number of global variables, and second, to reduce the number of local variables used in different functions. To reduce global variables, the different fields are moved into the general functions for reading and sending data via Simon. Then, C++ has a neat little feature called pass by reference. This means that instead of giving a copy of the value of a variable to a function call, the reference to that variable itself is given to a function call. This means that the function is able to modify this variable. The changes are then visible to the calling function. This idea is applied to all used functions where I deemed the change useful. Compiling gives the storage requirements of 2632 bytes of program storage and 307 bytes of dynamic storage. So overall an exchange of 4 bytes from dynamic to program storage and 1 free dynamic byte. This change is pretty mild, but at least something. Now onto the more interesting part. I played around with the minimum signal length a little bit and found out that I could reduce it from 1 millisecond down to 50 microseconds. You hit that right, I reduced it by a factor of 20. When we compare the recordings in Logic, the difference is wild. The new version now takes only 11 milliseconds for the transfer, that's 2.7% of the time for the original code. This is a very good improvement, but I have a feeling that the next improvements will be harder to achieve. Next up, I want to make the Simon protocol more usable. I find it very unfitting that there is currently lots of code in my Arduino sketch, and I know just the solution for it. To clean up this mess, I will shift over to using object-oriented programming. What this means is that I create two new files, a header file and a C++ file, where I move all the code from Simon into. This code is moved into a class defined in those new files. If you are wondering why I need to create two files for this, it's a C++ specific thing. In C++, a piece of code that shall be imported somewhere else needs to create a header file. This header file is required for the compiler because it needs to know all the different function and variable names before they are used somewhere else. What is actually happening during compilation is that the entire content of the header file is pasted to the line in the program where it is imported. This way, the compiler knows all names beforehand. Afterwards, the linker makes sense of the declared names in this space and the actual C++ file where the definition of the names is located. We could think of the header file as a blueprint for the source code that defines all the different interfaces and names of the code, and the C++ file as the actual code itself. I designed the Simon object in a way where during the creation of the object, the user can specify the minimum signal length and the size of the byte array. Then, There's another function called begin, where the user specifies the I/O pins for the data transfer. Using the code becomes significantly more easy by doing this, as you can see in this code comparison. After compilation, the results are quite surprising with 2620 bytes of program storage and only 47 bytes of dynamic storage. The dynamic storage surprised me. My guess is that this measurement cannot account for the storage an object occupies. This is supported by the fact that the amount of dynamic storage is less than the 100 bytes of storage for Simon that I specified here in the code. Regarding cycle times, I had to increase the minimum signal length up to 75 microseconds due to instability. I looked a bit into what might cause it in logic, and I saw different signal lengths during transfer. This gave me an idea for the last improvement that I want to make to the protocol in this video. I saved the best part to the final improvement, that is I/O register manipulation instead of using the easy to use digital read and digital write functions. Why? Because I want to and because I can learn a lot from it. So let's get into it. First, I want to show you what is actually going on in the code of digital read and digital write, because this teaches us a lot about how a microcontroller is actually interacting with its I/O pins. Let's go to the official GitHub repository for the digital read and digital write functions. You can see the code for the digital write function here. It takes the pin number and the new pin value as input parameters. There's seemingly a lot going on for just toggling a pin, for example some code to make sure PWM is running, or to check whether the given pin number is even valid at all. Before the pin state is changed, the current interrupt register state is saved and cleared to avoid jumping out of this function mid-switching. The actual switching is this if statement here. Afterwards, the interrupt register is reapplied. For the digital read function, the structure is similar in that first PWM and pin validity handling is done before doing the actual reading. When we look at both existing functions for pin manipulation again, we can notice that there's a lot of stuff going on that we actually don't care about during data transfer. I want to remove all of the overhead and just directly manipulate the I/O registers. At this point, a small warning: the code that you are about to witness is not for the faint of heart. I actually have some trouble reading it myself after not touching it for several months. I put the code from MK 1.4 next to the new code so that the comparison is easier. Judging just by the length of the send response function, you can see that the complexity increased a lot. I saved the pin registers at the initialization of the Simon protocol to avoid searching for them at each pin change. Since I know that the pin should be valid, I can skip any check and directly write to it. Looking at the send data function, it becomes clear why this is not done usually in Arduino programs. It is a mess and not readable at all. I can't even fit the total function onto my screen without reducing the font size. The read data function is especially bad, since I already used bit shifting and now I am also directly accessing the pin registers. If anyone is interested in the code, you can find it in my GitHub repo linked down below. That was a lot of deep dive information. Let's go back to simpler times where we just looked at our 3 measurements. Compiling gives us 2776 bytes of program storage and 62 bytes of dynamic storage, so overall actually a significant regression. However, using the registers directly, we can reduce the minimum signal length down to 40 microseconds, which gives us a total transmission time of just 8.3 milliseconds or 2% of the original transfer time. In my opinion, this trade-off is still worth it because a higher transfer speed is more important to me than storage requirements, especially when looking at which storage size the original program was. After going through all these improvements and changes of the protocol, let us look at the recordings of the original code and the newest version and compare them. Here you can see both, and we see that they look very different. The original code has a lot of changes on the data line, while the signal line stays constantly low. The new version is significantly more resourceful with pin changes. This comparison, like shown here, is interesting, but watch what happens if I adjust the timescales so that they match. It is really amazing to see that the new version manages to complete the entire communication in half of the time that the initial pin changing takes. The original code didn't even send a single bit of information by this point. Even better, the new code manages to send the entire message in the same time as the original code takes to send 4 bits of data. With this, I am happy with the performance of the protocol and I can continue to work on AAS in the future. The content of this video is actually a prep work for the next video of this series where I will rework the program to control the body of GLaDOS. I needed a properly working communication protocol first, which I now have. I can now continue with creating a more complex body program that can do lots of more better features, like more natural movements. I decided to switch up the structure of this video compared to my other videos. I want to slowly move away from the more rigid presentation style to a more natural flowing narrative. I think that this kind of style is more interactive, so I will try to slowly move more towards it. Anyway, thanks for watching this video and see you in the next one.